Okay, so we're recording. So now we're talking about oscillations with some harmonic motion doing springs. If you really want to look for information on that, 7.2 would be a good place. Hooke's law and some harmonic motion. We did talk about that last week we did waves. So anyway, if I open that file, force equals negative kx. You have energy in Hooke's law. And there's some other kind of things going on here with that. Anyway, so going back to this again, acceleration is constant. That actually won't be true. The restoring force is proportional to displacement. That is true. So force is proportional to displacement, which is x. We definitely know that's true. K is a constant. So 2 is definitely true. Acceleration being constant, that's kind of a weird one because you do have, like, you could have like something like hanging down like this. So you have acceleration due to gravity, but then you also have the acceleration kind of acting against it as well due to the spring, and it kind of depends what spring you're dealing with. So I don't think we can really say that. Is independent of the amplitude. Well, frequency, as we see here, is basically 1/2 pi, yeah, independent amplitude right there, times root k over m. M's the mass. So frequency won't depend on the amplitude at all. Amplitude is like how high the wave goes. So that's why it's going to be 2 and 3. So do study those notes. So it's D. But you know, it's open note anyway, so you have it all there for you. So organize your notes tonight for sure. So 1 is D. And again, the answer is in Schoology. Okay, now let's take a look at 3. A block attached to an ideal spring undergoes some harmonic motion about its equilibrium position x equals 0 with amplitude A. What fractional energy is in the form of kinetic energy in the block? Is at position of x equals half of A. Okay, so let's take a look at our potential energy, which is 1/2 kx squared. I don't know if we haven't really talked much about conservation of energy of springs. I don't know if that's really a fair question to ask you guys. But I suppose you could say this. So actually, we could do this. So your potential energy is that, right? 1/2 kx squared. So and I guess you could assume once that's equilibrium position, it's 100% potential energy. So what it means is that, let's say you have a spring. So you got a wall here. And you could stretch it out or you can compress it, but right now it's not moving. So there's no kinetic energy whatsoever. So it's 100% potential energy. And the formula for potential energy for a spring is 1/2 kx squared. Well, what happens is that if your position is now half of A, so let's assume our position right now was at x equals A. Because when it does get to its full amplitude, because what's going to happen is that, let's say you actually stretch it out. And that's going to be considered its full amplitude, x equals A. It's still also 100% potential energy. When it's fully stretched out. So your potential energy is 1/2 k times A squared. Now, if you take it to this, your potential energy is 1/2 K times 1/2 A squared, or now it's going to be 1/2 K times 1/4 A squared, or 1/8 A squared. So what happens is that you've lost 3/8. Or actually, a kind of better way of thinking about it is if you look at the ratio between this and this, now it becomes a 1-to-4 ratio. So it means that 3/4 was converted to kinetic energy. And that's why the answer is E. That's a tough one. I don't think I'm going to ask that one because I haven't really done that with you guys. But that's why the answer is E for 3. I think I might just ask straight up, hey, here's potential energy, we'll solve it. But yeah, I don't think I'm going to ask that. Let's take a look at 5. A spring block simple harmonic oscillator set so that oscillations are vertical. So that's going to look kind of like this. See how these oscillations are vertical here. The period of the motion is capital T. The spring block are taken to the surface of the moon where the gravitational acceleration is 1/6 of this value here. Okay. Then vertical oscillation will have a period of. So in this case, let's look at how periods impacted. Period is just simply, that's capital T here. That's just reciprocal this. This is 2 pi times the mass over K. Doesn't look like gravity actually impacts it. The spring constant matters, the mass matters, but it's not going to impact it. That's why the answer is D. It doesn't matter. So we don't worry about that at all. Seven. A block of mass M, 4 kilograms on a frictionless horizontal table is attached to one end of a spring of force constant K. And then it goes similar harmonic oscillator about equilibrium position X equals 0 with amplitude A equals 6 centimeters. And I'm not going to ask that. Let's cross that one off. We haven't done that. We'll cross that one off. Then let's take a look at 9. A simple pendulum swings about a vertical equilibrium position with angular displacement 5. Period T, the same pendulum is given a maximum angular displacement of 10 degrees, in which the following best gives. Yeah, we haven't done that either. So let's cross that one off too. Sorry, we haven't really done much with pendulum, so I don't think it's fair to ask you guys that. I think we could probably do 8. I'll have you guys take a look at 6, see if that's fair game. Maybe 4. Maybe 2. So let me have you guys. Yeah, let me think about this one here. So why don't you guys discuss yeah, I'm just trying to think for 1 sec. Yeah, let me have you guys do 2, 4, 6, 8 in groups. I'll give you guys about 6, 7 minutes, then we'll come back and talk about it. So 2, 4, 6, 8, don't do 10. 2, 4, 6, 8 oscillations. Again, this is in Schoology, so you guys could just download it and look it up there. So everyone should have this. And let me stop the recording.